Thank you for that great introduction. And so yeah, my lab is generally interested in lots of aspects of human learning. So we're interested in what controls the rate at which people learn new tasks, what controls their asymptotic level of performance, so who reaches what we would think of as true levels of expertise, who doesn't ever become an expert. But one of the big questions that we're interested in is what determines does learning generalize? And so we're kind of approaching this from lots of different directions, as you'll see, one of which is individual differences. And so there's obviously lots and lots of previous work, going back more than 100 years, examining individual differences in learning, the capacity to learn new tasks. So for instance, my students get sick of me making them read work by Thorndike in the early 1900s, who was already interested in this idea that there are big individual differences in learning. This was already known. And Thorndike argued that we could exploit the nature of those individual differences to learn something about their mechanistic underpinnings. So for instance, he argued that if what you saw as people learned was a divergence, so people kind of all start the same and then they diverge, well, that suggests that the underpinnings must be a little bit more biological, a little bit more nature, because if they're given the same experience and they pull apart, it suggests it's something inherent to them. Conversely, if they start very different and they pull together, well, given the same experience, everyone comes to the same place, suggests that some of these individual differences are due to experience or due to nurture. This is the idea that there's important individual differences that we can predict and that have real outcomes, also kind of inherent in all the work by Binet at the turn of the 20th century. So created the first intelligence task really by recognizing that there was individual differences in learning and asking what are the people who end up learning well in this context, in an academic context, what can the people who end up learning well in academics do that those who end up struggling in academics can't do? So how can we predict ahead of time who's going to be a good learner, with the idea that if we can predict ahead of time who's going to be a good learner, we can apply some remedial programs to kind of help people before they fall behind rather than to allow them to fall behind and then try to fix it. There was a host of kind of understanding that there was these predictable individual differences in military contexts really early on. So for instance, the US military had a general classification task in World War I that they used to assign people to different types of jobs. And this continued throughout, say, the 40s, where for World War II, the military created large prediction batteries, in particular around flight training success. Who can we put in the context of pilots or in radar operators? And then post-World War II, we start to see a lot of work kind of separated out by domain, asking about individual differences in learning and what predicts those individual differences in the capacity to learn. So for instance, Fleischmann in the 50s and 60s had proposed that there are 52 different unique abilities that can differ across individuals and that predict performance at different stages of the learning curve. So from when people are first exposed to a task, when they're kind of intermediate ability, and then finally what predicts their kind of asymptotic level of performance or their expertise. One thing that's notable, though, is kind of not all the fields had this strong distinction between what we think of as learning and learning generalization. So all fields in some ways have this, but where the line between what it means to learn a task and what it means to generalize your learning to a new task kind of differs from domain to domain. So one of the areas that I work most strongly in is in perceptual learning. And so in perceptual learning, there's often a really kind of sharp distinction that's drawn between kind of learning a task and then generalizing that learning beyond what you've learned, partially because in the data, there can be a really sharp disjunction between your capacity to do what you've learned and then your ability to kind of apply that broadly. So for instance, really classic work using the Bernier acuity task. So this is like the simplest possible perceptual task. It's alignment detection or offset detection. You're shown two lines, one on top of the other, and you just have to say, is the top line offset to the right or the left? This is obviously, really easy to say it's offset to the right, but you can make this arbitrarily difficult by reducing the size of the offset. And so often in perceptual learning, we'll just brute force the learning. We'll bring them for many, 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 many trials across many days. And if you just have someone do this task over and over and over again, they'll get better. So this is threshold, meaning the size of the offset that you can correctly detect. People will get better through time, right? And we see this in pretty much all perceptual learning. If you sit someone down, you have them do the task over and over again, they get better at it. What often tends to happen in perceptual learning is you get this really strong disjunction, though, when you ask them to do something else, something that might even seem conceptually similar. So, for instance, if it's the same task, but all we've done is rotate the lines by 90 degrees, now you have to say whether this line is above or below the left one. What you see in the data often is that you get zero carryover. They got better at the vertical task through time. And then the second you give them the horizontal task, they basically have to start back over and learn from scratch. And so because we often get this really sharp distinction between learning and generalization, it's a big focus in perceptual learning. In other domains, for instance, like education, this line is a lot more blurry. And so oftentimes it's not clear whether someone is really measuring learning or measuring learning generalization, because they're often kind of treated as part and parcel the same phenomena to some extent. In much of education, learning is about generalizing, and so doesn't really distinguish between, learning the initial thing and then generalizing that beyond what you've learned. And so because there's a lot of work on individual differences in learning, some of which is probably confounded with generalization, there's not a lot of work that's kind of specifically on differentiating between individual level predictors of the capacity to learn a first task and then individual level predictors of the capacity to generalize that learning beyond what you've learned. And so knowing whether or not there are these unique predictors between kind of the initial ability to learn and the ability to generalize, it has a lot of theoretical ramifications in terms of, what do we think about learning? What does it mean to generalize? Are these kind of the same phenomena? Is, learning generalization just a function of what you've learned, or is it separate? And then a lot of practical applications. So there are many practical applications for which you just want to predict how good someone's going to be at learning the base task. They're only ever going to have to do one task. They're not going to have to kind of move their skills to any new task. Increasingly, though, kind of especially in, say, 21st century jobs, almost everything is about generalization. You're constantly having to extend your knowledge to some new type of context. And so understanding whether there are, say, for instance, people who are disproportionately good at generalizing, or whether there are base cognitive abilities that predict generalization, not only is useful for kind of selection purposes. So, if you're the military and you're trying to select people for certain jobs, or for potential training, what are the targets that we want to enhance if we want to make people better generalizers? One way to get a hold on those things is via individual difference studies. And so what I'm going to be talking about today is some of this work that we've been kind of starting to try to separate out individual level predictors of learning from individual level predictors of generalization. And so, we're going to ask, are there individual differences in generalization? And are they different from individual differences in learning? And if so, as we'll see, they seem to be. Can we actually predict who's going to be a good generalizer, or what types of skills you need to generalize in different contexts? Are those different from learning? And do we see something that looks like a generalization trait? Are there people who can generally be good at generalizing? Or is it the case that this is very domain idiosyncratic, or at least domain specific? And so the first study I'm going to talk about is learning to fly mini-copters. And so when we're thinking through what methods we want to use to differentiate between kind of individual differences in learning and individual differences in generalization, this can be a challenge. First, we need to combine an individual difference study with a learning study, right? Both of these are difficult studies to do kind of on their own, right? For individual difference studies, you need lots of participants. For learning studies, it ends up being lots of hours. And so if you combine those, you have lots of participants doing lots of hours. So, my students, when they give talks on individual differences, they're like, oh, we have a sample size of 60, participants. compared to, say, colleagues in social psychology, who are doing survey work who might have individual different studies with 400 participants. But our individual different studies with 60 participants might represent 400 participant hours by itself. So it's challenging to do these types of studies, but we have to combine those two. We have to do individual differences combined with learning. It's also useful if we have really naive participants, and this ends up being challenging when we do work with adults. If we want to measure the full learning curve and then the full generalization, it's better if we have participants who aren't partway along the learning curve. We want to know the full learning curve. And adults often just don't start totally naive at tasks. They're starting with some types of abilities. So we wanted to think through, what is a task where we could measure a full learning curve and kind of full generalization. So the task that we're using for this is learning to fly a mini-copter. So you might know this as a drone. I learned very quickly that at the University of Wisconsin, I cannot call them drones because drones are banned on campus. And so if I call them a drone, they tell me I can't use them. If I call them a mini-copter, they're okay with it. It's also the case that, at least in the United States, drones are regulated by the FAA, the Flight Aviation Administration. And so all of this, as you'll see, is done in my lab. But if I call it a drone, my review board says, have you had this cleared with the FAA? And I say, I don't think they have jurisdiction over the airspace in my lab, which is on the 4th floor of a 6th floor building. But I did have to call them and confirm that they, in fact, don't regulate my airspace, which is great. So they're little mini-copters. They're, as you'll see, pretty challenging. We take participants who have never flown one before. So there are obviously people who have flown these, but we can easily select people who have never flown them. And unlike some types of real-world experience, there's actually still plenty of people who have never flown one of these. And so the way the study is going to progress is we're going to do kind of individual difference battery. So we're going to kind of measure a whole host of, as we'll see, kind of both cognitive, personality, lifestyle experiences. So we're going to measure speed of processing with a simple reaction time task. We're going to measure some aspects of attention and working memory, spatial cognition, fluid intelligence, depth perception, both in terms of things that we think might predict the initial capacity to learn, and also things that, as we'll see, might predict the capacity to do the types of generalization tasks that we're going to ask people to do. We also measured some personality aspects and things like video game experience, like previous experience with other kind of, say, types of technology that might predict the capacity to learn or to generalize. So that's session 1. They do a big individual difference battery. And then they do the learning component where they are going to learn to fly this mini-copter. And so we want to have this somewhat controlled. I was thinking through when I was prepping this talk, this is literally, I've studied learning now for, staff said, 25 years. It's the first time I've done a learning task that wasn't on a computer. And so has some challenges associated with it in terms of how we're actually going to track the learning and how are we going to make it analogous. And so what participants did in our learning task, they have a little course, so they're going to be flying through these loops. And so they're going to fly through the loops always in one direction. And so we have, as you'll see, we have 2 different courses that people could fly. So 2 different sets of loops that they're going to fly between. And there's 2 possible directions. And so this was fully counterbalanced across participants. Some of them flew track A, some flew track B, some flew counterclockwise, some flew clockwise. And that's going to come up for our generalization. So they did this for 4 sessions. And then on the last day, we do generalization. And the other reason that we liked this as a task is it actually allowed for a host of different types of generalization that we could ask about. So for instance, you could ask, after you've learned to fly one course, right, can you generalize your skills to some other course? Or is what you've learned very rigid for the course that you've learned? So here you can kind of see that these hoops aren't in the same position here as they are there. You're still flying in the same direction that you were trained in, but you're flying a different course. So it's generalization in terms of the course that you're flying. You can also ask about kind of a potentially simpler type of generalization where all we do is we take the exact same course, right? So this kind of configuration looks exactly like this one, except for this one is higher. And so there are some reasons why flying the drone up higher is different, but it's the same configuration. So once you get it to the right height, you could kind of continue to apply previous knowledge. So this is one where you should be able to apply a lot of your previous knowledge. It's pretty direct generalization. We think of it as near generalization. And then finally, we can ask people to fly the opposite direction. So they were trained on this course, they flew in one direction, and then during transfer, they fly the opposite direction. And so on the last day, participants come in and they do these 3 different generalization tasks. And this is going to allow us to differentiate between learning and generalization. So results. So one thing we wanted is people who are naive. We wanted them to be bad to start with because we wanted to track their full learning trajectory, as they said, and that is definitely the case. So they are incredibly bad at this when they start. Actually, most of the participants said that they would have quit almost immediately if they weren't there for 6 days, if they hadn't signed up for this as part of an experiment, because it could be really frustrating for participants at first. So I'll show a couple of videos showing what their behavior looks like right away, so you can see exactly how naive they are at this task. So this setup here, so this is the drone. You'll see my lab assistant over there, and the participant is actually sitting, they're standing behind this plexiglass, looking at the drone. So here's one example of an initial one. Right. And so this ends up being probably the most physically demanding experiment that my research assistants have to run. So one person's got a clipboard. They're actually going to be tracking the laps. And then there's a person you can't see over here whose only job is to run there and to pick the drone up and to put it back. And like they'll show me like their step counter after these. They get a lot of exercise going and picking these things up. So there's one. You can see here's another participant. They kind of get. I think that's the same one. Yep, here's a new one. Kind of get off. Right, they bang into it. There, right, there's a trial. And then this is probably my favorite video, showing exactly how bad they can be at this. So they fly, going okay, off screen. So the camera's kind of in the top corner of the lab. So wait a second. Oh, there it is. Right. It is not supposed to be up there. And it's actually why you can kind of see my lab assistants here. They're wearing a face mask and like hairnet. As we did this, we quickly realized the amount of protection that we needed to put in. I have like really strong memory of teaching one day. You know, I was in class, I was teaching, and an iMessage popped up that said, "Need help, drone stuck in participant hair." So they had flown it into their own head and it had gotten wound up in their hair. So yeah, we had to build in a whole host of protections. They've got plexiglass, they all wear masks, they wear hair nets. So they're very bad to start with. Okay. Because they're really bad to start with, you know, there's lots of room to learn, and they do learn kind of an incredible amount over this period of time. So it's really nice for a learning, you know, study because we get massive amounts of learning. It's really easy to track. So you can see here's one participant who's starting. This is like an early session for them. I think this is day 1 for this participant. You know, they're kind of working their way through. And you can see what they get to towards the end. You can see, you know, not necessarily fluent, but we'll see they're quite a bit better at this. Make it through perfectly fine. Right. So have some reasonable control over this. And obviously there's big differences in where people can get. So some participants, for instance, can get kind of outlandishly good at this. So this is one of the better participants. Right. And this is someone who started naive, but can get quite good at this through time. So we get big individual differences in our learning, which is nice. And so one thing that we had to think through for this task, unlike most of our learning tasks where we have like really easy, reaction time and accuracy, we have neither really accuracy or reaction time for this. And so the way that we're quantifying learning is via penalized lap times. So you can think of it just as a time where lower is better. But we have to apply some penalty so they're actually trying to do the task. They're trying to go through the hoops. So basically, we apply a penalty. Say if they miss the hoop, we add some time to their lap. If they crash, then we add some time based on basically extrapolating how long it would have taken them with some penalty associated with it. But all of the data is going to be in this penalized lap time. So lower is better performance. And so we see really good learning effects. Each one of these this is day 1, day 2, 3 through 5. So again, this score is lap times or penalized lap times. So lower is better. They get better through time. And what you can see, one of the more dominant effects, and it's not unusual in these types of multi-day studies, isn't necessarily the asymptote that they achieve at the end of the day, but it's how much they're carrying over. So you can see they get to a pretty good asymptote and then they kind of scallop back on day 2. They come back down, a little bit less fall off on day 3 to where we have far less fall off on day 5. They basically are stable in their performance. So these are the global performance. And then if we look at kind of the individual differences, we can see that we get pretty big individual differences in just this learning task. So some people start really bad. They don't improve that much. So we have at least one person who didn't really improve at all. Most people are improving through time, but with big differences between them. And it's really what we want if we're going to look at learning and generalization. We also get big differences across our 3 generalization tasks. And so increasing the height and doing a new course, people generalize pretty well. And then there's more difficulty when they have to go the opposite direction. So, and we can kind of see what it looks like for some participants here. So this is a different height. You can kind of see the way that we change the height is literally just put it on top of an extra box. So they're all, and so this is the same participant that you had seen before. They can do this pretty much the same way that they could do the task that they had learned. They kind of almost fully generalize. If we give them a new, now we'll just go to the opposite direction. So if you ask them to do the opposite direction, and again, this is the same participant who had been pretty fluent in doing the map in one way, you'll see they get pretty stuck at some point when they're trying to go the opposite direction. So they're kind of stuck over there and can't quite figure out how to make this turn. So you can almost like viscerally feel the difference between performance in the learned. So we can see there's kind of some generalization, right? They're better than they were to start with, but certainly not complete generalization here. Okay. So again, we get pretty big differences across these transfer tasks. So all of these, so the first 2 columns are the same. They're day 1 and day 5. And then our 3 transfer tasks. So for the changing the height and changing the pattern, changing the course, we get a lot of generalization. There's, as we'll see, individual differences in it, but we get a lot of generalization. And then when they have to move the opposite direction, we get a little bit less generalization. They struggle with that a little bit more. So kind of big questions. So, if we look at the individual differences in learning, we look at the individual differences in generalization, we end up with a ton of different parameters because we can ask, where do they start on the learning task? How quickly do they learn on the learning task? What's their asymptotic performance? And then the same for all of the generalization tasks. So just kind of give you a broad idea of the correlations. There are some correlations between how people perform the learning task and how they perform the generalization tasks. It ranges from, an R of 0.46, which is between their asymptotic capacity on the learning task and their asymptotic capacity on the new course. So basically, people who are good at reaching a good asymptote on the learning course also tend to reach a good asymptote for the new course. We might expect that. Right. But there's a whole host of these parameters that aren't super correlated with each other. So for instance, how quickly they learn aren't super correlated with each other. So there's some unique variance that comes just from the generalization task. It's not that generalization is just the same thing as learning. There's some extra variance to explain in how people are generalizing beyond just what they're learning. So for predictors of learning, part of the battery, or part of the reason why we picked the tasks we did in the battery was there are things that we've seen are predictive of individual differences in learning in visual motor tasks in the past. So some of the strongest effects included those that were related to spatial cognition. I'll go through some of these: spatial attention, speed of processing, fluid intelligence. They're things that are generally predictive of learning. So for instance, for spatial cognition, people who are good at mental rotation, this is the measure of spatial cognition that we used. Participants are shown these two stimuli, and their job is to say whether or not they're the same shape that's just been rotated, or it's been rotated and mirror reversed. So they're basically trying to mentally spin this thing around to say whether or not it's the same or not. For spatial attention, we use multiple object tracking, so they're having to track some number of targets that are moving around. It's really a spatial attention type of task. We use a very simple speed of processing task where they just see an arrow that's pressing or that's facing left or right. They press the corresponding button. It's about the purest measure of speed of processing you could come up with. And then for fluid intelligence, we use a matrix reasoning task. So this is the Raven's progressive matrices. So for instance, if we look at the correlations between, this is learning score, there's lots of ways that we can do these correlations. And it's actually a challenge to know what's the right measure to correlate with what. But we use learning score, which is just the difference between their starting and their end point. Multiple object tracking ends up being really kind of strongly related to total learning. The same with speed of processing. All these look pretty much the same for speed of processing, mental rotation, et cetera. Also, as Daphne mentioned, one thing we're interested in is video game experience. And so video game experience also really strongly related to this. And this kind of, makes intuitive sense. There's a lot of visual motor mapping that happens in video games. And so if you've learned to kind of effectively move your thumbs to control something external, it's actually really similar to what video games are. So what about predictors of generalization? And so all of our correlations, when we're looking at predictors of generalization, we're actually controlling for initial learning or learning on the first task. And so we kind of set this particular one up or this study up where our expectation was that, well, the capacity to generalize, we've set up different types of generalization tasks. One where you have to go in an opposite direction, one where you've got a different height, one where you have a new course. Well, if what generalization is taking your base learning abilities, and then you have to have something else to move to a generalization capacity, what might that something else be? And so, for instance, generalizing to a different height, the best predictor of kind of the capacity to generalize to a different height above and beyond learning is actually just simple depth perception. So we measure depth perception via these little stereoscopic glasses. So people who have good depth perception are good at this particular generalization above and beyond their capacity to do the base task, to do the learning task. So for the ability to do the opposite direction, we have a different best predictor, which is this mental rotation, this kind of spatial imagery type of task. So again, I forgot to mention the y-axis here is generalization cost. It's how much worse are you at the generalization task than you were at the initial task. So basically people who are good at mental rotation have very little cost. They have very little fall off in their capacity when they do the generalization task. Whereas people who have very poor mental rotation end up having a big cost. They're not good at the generalization task. And actually, video game experience predicted the capacity to generalize on all three, above and beyond the base learning. So what we see are, yes, we see clear individual differences in both learning and learning generalization. They share some variance, but there's enough unique variance that it's worthwhile asking whether we can uniquely predict the capacity to generalize from the capacity to learn. Some overlap in predictors, things like speed of processing and mental rotation were predictive of both the ability to learn and also the extra ability to generalize, whereas some of the others were unique to it, which suggests that we can get some leverage if we want to purposely produce generalization. So Next question. Can people be generally good at generalizing? So we can parcel this variance out. We can predict, who might be good at generalizing in this task. And our next question is, does this rise to something like a trait? Is there, in the same way people think of fluid intelligence as, well, in many cases, the capacity to learn, and that is somewhat trait level. There's usually some domain aspects in it. Is this true of the capacity to generalize? And so, yep. So here what we're going to do is the same kind of idea. We're going to combine individual differences with learning. We're actually going to do two different learning and generalization tasks. And what we're going to ask is, were the people who are good at generalizing their learning from one task also good at generalizing their learning from a second task? So methods here, same basic idea. So session one, we do a big individual difference battery. Same kinds of tasks, they're not identical. Session two, they did 3 blocks of training on a perceptual task, and I'll go through what the tasks are here in a second. Session three, they're going to do 1 block of basically retraining on that first task that they trained on the day before, and then they're going to do a block of generalization. And they're also going to do some training on task 2. And then finally, they're going to come in on the 4th session and do 1 block of retraining and then a block of generalization. So from this design, we have 2 different tasks that we can both measure learning and measure learning generalization, and then also a bunch of possible predictors. So our 2 tasks were situated in the perceptual kind of learning literature, and we picked them because we already a priori knew that there was individual differences in how widely people generalize their knowledge. We hadn't examined whether there was kind of any predictability about that, but we at least knew that there was differences in it. So one is a texture oddball task. So what participants see is just a blank screen. They get an orienting tone telling them that a stimulus display is going to come on, and then they see the stimulus display. Their job is to say yes or no, is there an oddball element in this? So half the time there's an oddball element that's oriented at a different orientation than the kind of background texture. Half the time there's not. And then they get a mask and they have to say, were all the lines the same or was one different? And what we're kind of measuring is the capacity to identify that oddball at different amounts of SOA, so time between the presentation of the stimulus and presentation of the mask. And so for training, participants would see 1 orientation for the background and 1 orientation for the target, and then generalization, those orientations would be flipped. So the orientations that were previously the targets are now the background. Orientation that was the target, or that was the background, is now the target. And that's kind of another constraint that we tend to have for these types of studies is you want to have your training task and your generalization task be roughly equivalently equal. It becomes really difficult to kind of attribute the variance if there's big differences in difficulty across the tasks. So this is nice. There's kind of no reason to think these 2 tasks would be different from one another, and they tend not to be. Our second task was, again, in the perceptual domain. It was motion direction discrimination. So participants saw a kind of field of dynamically moving dots. They were kind of the direction was uniformly chosen from a distribution centered on 45 degrees. So they would see one particular kind of direction of motion. They would then see kind of all the dots randomly moving as a mask. And then their job was to say, do I think that the dots were kind of moving above the diagonal? So they would press the up key, or do I think it was moving below? So kind of rotated more horizontal from the diagonal. They would press down. And so here again, we have our training task. It was all the dots were centered on this kind of 45-degree diagonal. So they're all kind of say going up and right from my perspective. And then the diagonal, they were going to the other top corner, or sorry, for the generalization, they were going to the other diagonal, the other top corner. So first, talk through, do we get good learning and generalization? So for the texture oddball task, so the y-axis here is threshold again. And so we see good learning, people get better through time. And then for the generalization, we see kind of part generalization. They fall off some, but not completely. We see this for the dot learning as well. People get better through time. This one, it's not clear that the average participant has actually shown any generalization. And we'll see this in the next study as well. But there's certainly differences in that. I'm going to flip through those just given time. So first question, do we see correlations in learning? Are people who are good at learning perceptual learning task 1 also good at perceptual learning task 2? And so these 3 plots are different parameters in our learning function. So the furthest left plot is, did the people who started good at task 1 also start good at task 2? We can see not really the case. And we've actually observed this in a number of learning studies, that where people start tends to be pretty idiosyncratic. It's consistent with the idea that people come to the lab with really different types of experience. And so it's hard to predict how good they're going to do at one perceptual task from another perceptual task. On the other hand, their capacity to learn, so this is the rate of learning. It's not exactly the derivative of this function, but something like that. How quickly they're learning these tasks is actually really correlated. So this is task 1 and task 2. So we get a really strong positive correlation. People who learn quickly on the texture task also learn quickly on the motion task. And the third plot is asymptotic performance. So people who reach a good asymptote on the orientation task also reach a good asymptote on the motion task, and vice versa for those who are poor at it. So the bigger question, this is something that we would have expected ahead of time. There's at least some amount of work in perceptual learning that suggests that the ability to learn a perceptual task is correlated across a lot of perceptual tasks. What was less well known, or actually not known, is whether there was correlations in the capacity to generalize. And so again, all of these are controlling for initial learning. It's the same 3 parameters though. Are people starting in a good place on the generalization task, controlling for where they started on the learning task in task 1 and task 2. We can see those are actually pretty strongly correlated. So people who start good on the generalization task for oddball, for the visual oddball, also start better for the motion. A correlation for the learning, although it's kind of a weird distribution and not totally sure why that's true, partially because it's just difficult to estimate the learning rate for the generalization because they do so few trials. It's hard to get a good measure of exactly how fast they're learning. We can get more accurate measures of where they start and where they end. We actually see very little correlation, though, between their asymptotes. So the strongest correlation is actually that immediate generalization versus where they end up after controlling for the learning. Most of the variance on where they end up on the generalization task is actually sucked up by the variance where they end up on the learning task. It doesn't seem to be unique. So then in terms of predictors, we end up with kind of some similar predictors. I'm not going to go through the whole giant table, but for instance, again, speed of processing tends to be predictive of the capacity to learn in the perceptual domain. It's by far the strongest predictor for us. It's predictive of where people start, how fast they learn, and where they end up. What was the bigger question for us is what would be then predicting generalization after controlling for learning? And what we saw, speed of processing still ends up being a really strong predictor. People who just have faster reaction times also seem to generalize better above and beyond their capacity to learn better. But we also see, for instance, task switching, the ability to kind of be flexible with your visual motor behavior ends up being predictive of the capacity to generalize in this context, right? You're kind of switching up some things about this task, both for the oddball and the motion, but not others. And so people who have lower switch costs, meaning they're less kind of thrown off by going from task to task, also we see this in their capacity to generalize. So within a domain, within this perceptual domain, we have kind of really similar results as we saw with the mini-copter. So learning capacity and generalization capacity somewhat correlated, but again, there's some unique variance in terms of the capacity to generalize. And the predictors of the capacity to generalize are somewhat shared, but also some new predictors that could be targets for training. And so the last study kind of asking how far can we push this? This is something that's been, say, a big debate in the intelligence literature basically for as long as there has been in intelligence literature is there one intelligence, which people will sometimes think of as the capacity to learn, or are there a host of different intelligences? People learn better in some domains than others, and it's really domain-specific capacities. Can ask whether this is similar for generalization. And so we're going to do a really similar study, but have one task that's in the perceptual domain. It's the same one, the stop motion task that we used in the last study. And then we wanted something that was far apart, so same training, same generalization, something that was far from perception, something that kind of fit in the traditional learning literature, so often something academic. And so for us, using a task that was academic was actually somewhat challenging because to do all the analysis that we want to do, we need a trial structure where there's, trial by trial, we can measure accuracy, we can measure reaction time. And we need training and generalization tasks that are somewhat symmetrical. They're somewhat similar in terms of level of difficulty so that we can kind of uniquely parcel out the variance that's due to learning and due to generalization without having big differences in difficulty confounding that. And so the task that we ended up settling on was a math task. And it was having people add in alternate bases. So rather than base 10 that we're all used to, they were learning to add in different bases. And so, since we give them a little introduction first about adding, say, in base 6, and then we would just kind of do the same thing that we do for perceptual learning. We brute force this. We give them trial after trial after trial of base 6 addition, and they either get correct feedback, incorrect feedback. We give them some additional information. So if they aren't respecting the rules of base 6, so obviously in base 6, you can't have the number 6. We tell them this is base 6. You can't use those digits in this. And so this is nice as a learning task because, in some pilot work, we found that adding in base 6 and adding in base 8, basically the same level of difficulty. But there is the potential for seeing some generalization. If you've learned to add in base 6, you can imagine some kind of capacities that might allow you to carry that over and add better in base 8. So methods end up being really similar to the ones that you've seen. First day, we actually did a lot of our training. So they did 250 of the base 6 addition questions. They're doing 250 just because it takes them far longer to do those than the 600 dot motion task trials that they can do. They can get through those trials far faster. And then on day 2, again, we do a little bit of retraining. So for instance, they retrain on whatever they initially did. So we're counterbalancing whether they're initially trained on base 8 and then generalized to base 6, vice versa. So they would do basically a little bit of retraining on day 2 on whatever they had done on day 1. And then they do the generalization. We swap them, say, to base 8. And then the same thing for the motion. So results. So one thing that, wasn't necessarily obvious when we started the project is that we would get results that look like those we've seen in perception. When we do this math task, it's just not typically the way that people do training in any kind of academic context. Turns out that we can get really similar types of results. So this is response time. Participants were actually pretty accurate. We had very low error rates. If we decide to add error rate into the analysis, it doesn't really do anything. So this is just response time by block. So people are getting definitely better through time. They're getting more fluent is how we would think of it. They're faster. They're not really changing their accuracy. And then when we swap over to, yes, this is individual differences. So pretty much everyone gets better at this. And then when we swap over, we see this kind of partial generalization. They kind of carry over some. They're not as bad as when they started the initial training, but they have some amount of failure to fully generalize. So, those are. And what we also wanted to see is that there's some difference or some individual differences in the ability to generalize. And we see that pretty strongly. So there's some participants, from block one to this is their very first block of training, and this is their very first block of transfer. We actually see they're kind of carrying over a lot of information. See some that aren't carrying over any. And we actually see in some participants negative transfer. It's something that we're interested in, basically meaning that they're worse at the beginning of their transfer block than they were at the beginning of their training block. And so this has got some interesting theory associated with it. There are things that people could be learning in the first task that in practice would make it hard to learn the second task. And so something that we're interested in. But for the purpose of this talk, we see good spread in learning generalization. And then the same for the dot motion task. So just like before, this is threshold. People get better through time. Everyone gets better through time for the most part. And then when we do the transfer, they actually, again, at the population level are showing what we would think of as specificity. They're not generalizing at the population level, but within participants, we see pretty good mixtures. We see some people who are better, some who are about the same, and some who are worse. Okay. So the correlations, just like before, if there's truly a shared capacity to generalize that extends as far as between perception and academics, we kind of expect this linear correlation, this positive correlation that we saw for the two perceptual tasks. Lots of the work on intelligence would put academic learning and perceptual spatial learning in separate domains, in which case the prediction would be not much shared capacity to learn and probably not much shared capacity to generalize. And it is the latter that we see. So unlike the perceptual learning where we see really strong correlations, this is just for the generalization ability for the two. These are basically uncorrelated. And this, I think, this was at the beginning of the semester. We just finished the full data collection for this, so we're up to 60 participants. I don't really expect this will suddenly become a strong positive relationship. My expectation is it's actually probably zero. So basically, once we moved to pretty disparate domains, we no longer saw this shared capacity to generalize. We saw some people were good at generalizing in math and some people were good at generalizing in perception, but they were not necessarily the same people. So this is more suggestive, again, of something like that multiple intelligences perspective on learning, just applied to generalization, where the capacity to generalize is somewhat situated within domains. So broad conclusions, we can separate out the capacity to learn from the capacity to generalize. We can think through what abilities might be disproportionately useful for generalizing in some domains versus other domains. And we're already thinking about how we might test whether or not those relationships are causal. Can we improve certain capacities and through that improve people's capacity to generalize? But it does seem to be situated within domains. And so another question that we're interested in is, well, how far apart? To some extent, it's a little bit circular, asking, well, things correlate, they must be a domain, but it's actually how a lot of the initial history around intelligence work as well. So we've got several ongoing studies where we're testing, things that we might think are in between academic learning and perceptual learning in some space. So for instance, things that have to do with spatial visualization. So that is it for me. Just want to thank my lab. These are all my grad students. Some of you probably know Aaron Cochran. He was one of the primary authors on that second study. And I'm happy to take questions. So thank you.